We continue with part 2 of lecture 23. I said I'm just going to work out one example in this part. I was thinking of doing example 3 from lecture notes, from lecture 23, from lecture notes, which I shared in OT class. It's a long example, and you can read the whole example from the lecture notes. So instead of doing that example, I decided to do parts of it as separate examples, and then you can collect these parts and read this example from the lecture notes. So I will do parts of example 3. Okay, so the first part is to find the inverse Laplace transform of the function s plus 1 divided by s squared plus s plus 1. Which function would have its Laplace transform equal to s plus 1 divided by s squared plus s plus 1. All right, in general, to figure out this inverse Laplace transform, we apply partial fractions, so we try to factor out the denominator. But the thing is, s squared plus s plus 1 has no real roots, so it cannot be factored out in real numbers. What do we do in this case? So we try to write s squared plus s plus 1. We try to complete it to a square. So since we have s squared plus s, we try to write it as s plus 1/2 squared. If you take s plus 1/2 squared, it would be s squared plus s plus 1/4. But on the left side, we should have 1. So from 1/4 to get 1, we need to add 3/4. Okay. So since we have s plus 1/2, it means we have a shift by minus 1/2. But in order to see this shift, we should also have s plus 1/2 in the numerator. So the numerator we write as s plus 1/2, but in the numerator we have s plus 1. So to get 1 to s plus 1/2, we should add another 1/2. And we divide this fraction into 2 parts. The part with the numerator s plus 1/2, and the part where the numerator is just 1/2. All right, now for the first one, first we consider s over s squared plus 3/4. This is the Laplace transform of cosine √3/2t, right? If you take the number a to be √3/2, its square would be 3/4. So its Laplace transform would be s over s squared plus 3/4. But instead of s, now we have s plus 1/2. So this is the Laplace transform. So in the transform, we shift s by -1/2. So that means on the t world, on the t space, on the function side, we multiply with e to the -1/2 times t cosine. And I'm using the formula that Laplace transform of e to the at times any function is capital F of s minus a, where capital F is the Laplace transform of f. So since the Laplace transform of cosine √3/2t is s over s squared plus 3/4, when I multiply cosine √3/2t with e to the -1/2 times t, on the other side, on the s side, we shift s by -1/2. So we have, instead of s, we have s plus 1/2. All right, so similarly, for the second part, if we have 1 over s squared plus 3/4, this is the Laplace transform of, I want to take sine of √3/2t, but remember for the sine function, when you take the Laplace transform of the sine function, in the numerator, you get a. A here is √3/2. So I need to multiply by 2/√3 because on the left side, the numerator is just 1. Okay, so if I shift s by 1/2, then my function, I need to multiply with e to the minus t/2. -1/2 times t means minus t/2. 2/√3 sine √3/2t. Okay, so if I combine here, let me call this equation 1, and this last one, equation 2. Now, 1 and 2 implies that this inverse Laplace of s plus 1 over s squared plus s plus 1 is equal to, from equation 1, we have e to the minus t/2 cosine √3/2t plus, for the second part, I have the coefficient 1/2, and in equation 2, I have the coefficient 2/3. So the coefficient becomes, not 2/3, 2/√3. So the coefficient becomes 1/√3 e to the minus t/2 sine √3/2t. Okay. Now, in the second part, I will try to find the inverse Laplace of, for any number a, inverse Laplace of s over s squared plus a squared squared. Now, we know that if you take just s over s squared plus a squared, this would be what? cosine of 80, right? We know this one. But what if we have square? All right. Also, we know that inverse of 1 over s squared plus a squared, 1 over a sine 80. Because in the Laplace transform of sine 80, we have a in the numerator. Okay, so from here, how do I get the inverse Laplace of this? So in the denominator, instead of s squared plus a squared, I want s squared plus a squared squared. Okay, so what I do to obtain this, what I'm going to do is I'm going to take the derivative of 1 over s squared plus a squared. What is the derivative? Usual derivative with respect to s. So it is minus the denominator, the numerator is just 1. So the derivative is minus denominator's derivative, which is 2s, divided by denominator squared. So I can write the function s over s squared plus a squared squared as minus 1/2 times the derivative of 1 over s squared plus a squared. But 1 over s squared plus a squared is the Laplace transform of cosine 80. Laplace transform of 1 over a sine 80. Now, taking the derivative of the Laplace transform means taking negative of the Laplace transform of t times the function. So here I recall that Laplace transform of t times f of t is minus the derivative with respect to s of Laplace transform of f of t. So this is what I'm using here. Okay, so the derivative with respect to s, is minus the Laplace transform of t times the function. So if you continue from here, we have 1/2 is constant. I can take it inside. Minus minus, it's plus. So Laplace transform of 1 over 2a t sine a t. Okay, well, that means I started with s over s squared plus a squared squared. So this means the inverse Laplace of s over s squared plus a squared square is 1 over 2a t sine a t. Okay, so taking the derivative on the s side corresponds to taking the function times minus t, or yeah, minus the Laplace transform, but minus sign, you can take it inside the Laplace transform. So taking derivative with respect to s on the s side corresponds to multiplication with minus t on the t side. Okay. We don't have a minus sign here because the derivative of 1 over s squared plus a squared already has a minus sign. So the two minus signs kind of cancel each other out. Okay. Now, the third part, similar. So instead of s, what if we have just 1 in the numerator? And again, the denominator is s squared plus a squared squared. Again, I'm going to solve it similarly by taking the derivative. For s, I took the derivative of 1 over s squared plus a squared. For 1, I'm going to take the derivative of s over s squared plus a squared. Okay, so what is the derivative? Derivative of the numerator now is 1 times the denominator minus the numerator times derivative of the denominator over denominator squared. So this derivative is a squared minus s squared. Now I'm going to do a little bit of manipulation and write this as, instead of a squared, I'm going to write 2a squared minus a squared. But with this manipulation, it becomes, I'm going to divide my fraction at 2a squared. But then the other two parts both have negative signs. So if I take out the negative, I have a squared plus s squared. So I can make a simplification in the second fraction. I have 1 over s squared plus a squared. So I need the term 1 over s squared plus a squared squared. So I solve it from here. So 2a squared divided by s squared plus a squared squared is equal to. I take this next term to the other side with the plus sign. And also I have the derivative of s over s squared plus a squared. Now, 1 over s squared plus a squared is the Laplace transform of 1 over a sine at. And s over s squared plus a squared is the Laplace transform of cosine at. Okay. But taking the derivative with respect to t, remember, means multiplying the function on the other side with minus t. We have a minus sign, and the function cosine at we multiply by t. So this is Laplace transform 1 over a sine at minus t cosine at. So Laplace inverse of 2a squared over s squared plus a squared squared is 1 over a sine at minus t cosine at. And if you want just 1 over s squared plus a squared squared, you need to divide by 1 over 2a squared. You need to divide by 2a squared. It's just a constant, so you can take the constants in and out of Laplace transform and inverse Laplace transform. All right. Now I'm going to use the results of parts 2 and 3 for specific value of A. Okay. Okay, let me write it. So next part 4. What is the inverse Laplace of s plus 1 divided by s squared plus s plus 1 squared? All right. Now, again, s squared plus s plus 1 cannot be factored out. So I completed to a square. It is s plus 1/2 squared plus 3/4. So I have a shift by minus 1/2. So in the numerator, I also need a shift by minus 1/2. So s plus 1, I write as s plus 1/2. Plus, to get s plus 1 to s plus 1/2, I need to add a 1/2. Okay, so for this one, we apply result of the second part, result of 2, with a equals √3/2 and shift by minus 1/2. Since we have a shift with minus 1/2, I take e to the minus t/2. And then when I forget about the shift, I use the result of result of part 2 with the number a equals √3/2. So if we go back up to part 2, this is part 2. So for a now, I have square root of 3/2. So 1/2a t sine at. 1/2a. A is √3/2. T. Let me just check. Yes, 1/2a t sine at, √3/2 t. Okay, so 1/√3 e to the minus t/2 t. Oh, I'm sorry, this is only the first part. I also have, sorry, I need to continue, plus. This is just the first part. For the second part, we apply result of 3 with, again, a equals √3/2 and shift. Shift by minus 1/2. So again, since I have a shift by minus 1/2, I have e to the minus t/2. Oh, I have 1/2 in front of everything. I have the coefficient 1/2 first. Shift by minus 1/2, so e to the minus t/2. Then I apply the result of part 3. The result of part 3 has 2 terms in it. Or let's check part 3. Yes, 2 terms. And in front, we have 1/2a squared. So 1 over 2 a squared, 1 over 2 a squared is 3 over 4 times, let's see, 1 over a sine 80, 1 over a. 1 over a is root 3 over 2, sine root 3 over 2 t. And then let me check the result here. Minus t cosine 80. Minus t cosine root 3 over 2 t. Yes. So if I simplify, I have e to the minus t over 2 in front of everything. In the first part, I have 1 over root 3 t sine root 3 over 2 t. And then, okay, 2 over plus 2 over 3 root 3 sine root 3 over 2 t minus 3 minus 1/3. Wait a minute. Yes, minus 1/3 t cosine root 3 over 2 t. Let me check. Yes. Okay. Now, let me call this function h of t. Okay. It is the, let me rewrite. This is the Laplace inverse of s plus 1 divided by s squared plus s plus 1 squared. So in s squared plus s plus 1 cannot be factored out, so I complete it to a square. It corresponds to a shift by minus 1/2. So on the t side, I multiply with e to the minus t over 2. Now for the next part, what if I multiply this function with an exponential, e to the minus 100s times s plus 1 divided by s squared plus s plus 1 squared. So in part 4, we computed the Laplace inverse of s plus 1 divided by this thing. And now I'm asking what is the inverse Laplace of the same thing multiplied by e to the minus 100s. So we have the shift by minus 1/2. So on the t side, we have the function e to the minus t over 2. But now on the s side, I multiply with e to the minus 100s. So remember, this means on the t side, I need to take unit step function at 100, and I shift the function, which is the Laplace inverse of the remaining part, ht, which we figured out in part 4. In this part, we shift t by 100. Okay, so this is going to be u 100t. In h of t, which is about here, this is h of t, I replace t with t minus 100. So e to the minus t minus 100 divided by 2. Maybe I should continue on the other page. Don't forget the h here. Let me see, where's my h? Yes, okay. 2 over, yeah, okay. So let me continue in the next page. U 100t. In the function h, I replace t with t minus 100. So minus t minus 100 over 2 times 1 over root 3 t. But instead of t, I use t minus 100 sine root 3 over 2 t, but instead of t, I use t minus 100. Plus 2 over 3 root 3 sine root 3 over 2 t, but instead of t, I use t minus 100 minus 1/3 t, but for instead of t, I use t minus 100 cosine root 3 over 2 t, but instead of t, we use t minus 100. Okay, so this is the Laplace inverse of e to the minus 100s, s plus 1 divided by s squared plus s plus 1 squared. Okay, now in the final part, which one was this? Part 5. So part 6. If you read through the example, it comes in one part, we need to find the Laplace inverse of the function 1 over s times s to the 4 plus 2s cubed plus 3s squared plus 2s plus 1. Okay. Now, it's a rational function, so I need to use partial fractions. But before partial fractions, the second part in the second factor in the denominator, this 4th degree polynomial, I should try to factor it out. As it turns out, it doesn't have any real roots. How do you see that? How do you see that it doesn't have any real roots? You try to find a real root, you try some numbers, you see that you always come up with a positive number. It doesn't matter which value of s you use, you keep coming up with a positive number. Never get to a negative number, okay? Because we have s to the 4 plus 3s squared plus 1, and that's a big positive number. And the other two terms, 2s cubed plus 2s, even if you take s negative, those two terms are not enough to compensate for the positive terms. So what do we do? Okay, it doesn't have any real roots, but still we may be able to factor it out into two degree 2 polynomials. And in fact, this polynomial is the square of s squared plus s plus 1. I guess you just come up with this by practice, but what you can try when you see that s to the 4 plus 3 plus 2s cubed plus 3s squared plus 2s plus 1 has no real roots, try to write your polynomial as the product of two degree 2 polynomials. So s squared plus some number a times s plus some number b times, again, s squared plus some number c times s plus a number d. And when you try to do this, you will see that all of those numbers has to be 1. Okay, so your polynomial is the square of s squared plus s plus 1. All right, so using partial fractions then, we try to write this as number a over s. In the next one, the denominator is s squared plus s plus 1. So in the numerator, we take something of degree 1, so a bs plus c. And the last term is s squared plus s plus 1 squared. But since the same denominator as the previous term repeated, it's s squared plus s plus 1 squared, in the numerator, again, we take something of first degree, bs plus e. You remember this from partial fractions. Okay, so when we try to find the numbers, we get the common denominator. So we multiply the number a with s squared plus s plus 1 squared. We multiply the numerator bs plus c with s times s squared plus s plus 1. And the denominator ds plus e with s. And this whole thing should be 1. I'm going to leave this computation to you, how to get the equations, how to find the numbers. As it turns out, the number a has to be 1, and all other numbers are -1. You can fill in the details. You can figure out the constants yourselves. So that this fraction is 1 over s. In the next fraction, both b and c are -1. So I take out the minus sign to the front. We have s plus 1 over s squared plus s plus 1. And in the last one, again, both of them are -1. So I take out the minus sign, s plus 1 over s squared plus s plus 1 squared. And now to find inverse Laplace of this. Inverse Laplace of 1 over s is 1 minus inverse Laplace of s plus 1 divided by s squared plus s plus 1 is the first part we did in this lecture. Look at the very first part. It is e to the minus t over 2 times cosine of root 3 over 2 t plus 1 over root 3 sine root 3 over 2 t. And the last part we did in part, let me see, in part 4, inverse Laplace of s plus 1 divided by s squared plus s plus 1 squared. We did it part 4. It is e to the minus t over 2 times 1 over root 3 t sine root 3 over 2 t plus 2 over 3 root 3 sine root 3 over 2 t minus 1/3 t cosine root 3 over 2 t. So this is from part 1. And this is from part 4. Okay, there is one last part in this example. I will just write it in the short way. This function, the inverse Laplace of this thing, let's call this some function. Did I use G anywhere? Hope not. Let's say this function is g of t. Then the last part, what was this part? Part 6. So part 7. What is the inverse Laplace of e to the minus 100s divided by s times this thing? E to the minus 100s means we take unit step function at 100 and inverse Laplace of the remaining function, which we did in part 6, the function g of t. In the function g, we shift t by 100. I'm not going to write out the final result, but so in g here, this is g, you replace t with t minus 100. Okay. Okay. So this example then finishes lecture 23. We have just one more lecture in Laplace transforms. Next lecture, lecture 24. We need to cover just, well, 2 more things, really. We need to cover, okay, 2 more things in Laplace transform. We need to find Laplace transform of what we call impulse functions. And we need to cover convolutions. Convolutions are going to be, okay, we know that Laplace and inverse Laplace are linear, but we don't know how it behaves under multiplication. So convolution is going to give you the Laplace inverse of the product of 2 functions. So one function is the Laplace of something. The second function is Laplace of something else. And what happens when you multiply them? How do you get their Laplace inverse of the product? So this is with the convolution integral. So those 2 we are going to cover in lecture 24. Okay, until then.